Okay, this is Griffiths Intro to Quantum Mechanics problem 2.6. This is a really long one, so I'm probably going to just do A, B, and C in one video and then do the rest of it in the next video. Just to break it up so it's not like an hour. It'll probably still be long though. My original solution is about 6 pages, so let's go ahead and start with A. So for A, I want to normalize this wave function that I have at time equals 0 to be normalization constant times wave function 1 plus wave function 2. So we have some superposition of two waves, some complex thing there. So we had like psi 1 plus psi 2. And they add together, as all waves do. So this is at time equal to 0, so t equals 0. And from earlier sections, we know that we are allowed to go ahead and normalize it at time equal to 0, and that it's going to stay normalized. Alright, so let's go ahead and go with our equation to normalize, which is in general over all space x. We have a probability of finding our particle somewhere. So let's go ahead and plug this in. That's going to be a squared. That'll be from negative infinity to infinity. I don't have any specific limits here. We're integrating over x. And then we have psi 1 plus psi 2. And I'm just going to go and put that in absolute values squared. Okay, we can go ahead and parse that out using good old FOIL. So I get psi 1 squared plus psi 1 psi 2, psi 1 psi 2 plus psi 2 squared. So just using regular old FOIL, nothing too complicated. And now we're going to have our general wave function. So this is a particle in an infinite square well. So now that we've worked it out in general, now we're going to look at our square well, which we could say from 0 to a. You could also do negative a to a, or negative a over 2 to a over 2. I think it's easiest just to do 0 to a. And we have a couple of wave functions trapped in there, and then we have whatever superposition of them. We can use our result of a wave function trapped in a square well. We know what the shape of that is. We know that it's a sine wave. We've done this before. So I'm using the width A. And my normalization constant here. And this I know from my boundary conditions. So I should probably draw that a little bit better there. Regardless of whatever shapes these waves are in here, we have to meet these conditions that it is 0 at 0 and it is 0 at A. So we know that it's periodic, which means that we know that it's a wave function. So since we know the general shape here, what we're looking at is really just two different states. So we have a state of the wave function in 1 and a state of the wave function in 2. So we know that the wave function has to be a sine wave, meaning that psi 1 and psi 2 are different excited states of that wave function. So that just means, for simplicity, we might as well just be looking at, say, n equals 1 and n equals 2. We could choose any two arbitrary states that we wanted to, but we might as well look at these two. It's going to be a lot easier. We could do 2 and 3 or 3 and 4, but there's just no real point to that. Okay, now looking at this guy, if I break that up into different integrals, whoops. And now we're going to be going from 0 to a, so I have this plus this integral plus this. But from an earlier problem, we found that the wave function is orthogonal, meaning that if we try to integrate to mixed states like here, then we find that they get a 0. So that just means that we have our first state plus our next state. So we have a probability of 1 of finding our particle in the well. But we have different probabilities of finding it in excited state 1 versus finding it in excited state 2. Those two probabilities added together equal to 100%. So basically, we know that our particle is inside the well somewhere. We know that it exists, we know that it's trapped in the well, and we know that it is in either state 1 or state 2. So let's go ahead and work out those probabilities. Now I do still have this other capital A normalization constant out there, but I'm going to have from 0 to a dx, and then psi 1 is going to be 2 over a, and I'm just going to go ahead and use n equals 1. And then I have from 0 to a dx 2 over a, and now I'm going to use n equals 2. Oh, sine squared, and then that is going to be squared. Okay, so now I have 1, and that's going to equal a squared, and then we have 2 over a, and then it's going to be times these integrals. Then, since we've been doing this sine squared integral a lot, I'm just going to pull up the result from an integral table here, which I've used several times before. So the integral of sine squared x just equals x over 2 minus 1/4 sine 2x. So I'm going to go ahead and do a couple of u substitutions here. My first u substitution is going to be u equals pi over ax, meaning that du dx is just going to be pi over a. So dx equals du a over pi. My limits are u1, so my lower limit is 0 because I just plug in x equals 0 for u1. My second limit, u2, I have pi over a times a, so it's just pi. Now my second u substitution, I'm going to write v, and that's going to be 2 pi over ax. So my dx is just going to be du, and then that'll be a over 2 pi. And then my limits are going to be, v1 is just going to be 0, but v2 is going to have that extra factor of 2 in there because it's 2 pi over a, so it's just 2 pi. I know you could just use Wolfram Alpha for that. I find it easier to just do the u substitution. Okay, so now we have from 0 to pi. I have du, we have an a over pi out there, and then that's sine squared u plus 0 to 2 pi, and then I have du, meaning I have an a over 2 pi. You can see that these are gonna cancel out anyway. I guess I should write v and then v. Okay, now using my integral table result there, I have one equals a squared 2 over a, and then we have, I'm just going to leave these out here, a over pi, and then we have u over 2 minus 1/4 sine 2u from 0 to pi. So you see that sine term's just going to go away. Same with this one too. So I get v over 2 minus 1/4 sine 2v, and that's from 0 to 2 pi. So both these signs go away. At 0, they go away. So we are left with just the pi terms there. So then we have, I'm going to go ahead and move this guy over. So I get a over 2 equals a squared, and then we have a over pi minus pi over 2 plus a over 2 pi. It's 2 pi over 2. And I should really put absolute values there. Okay, so that's gonna simplify quite nicely, as we can see, which is usually what you want to see in textbook problems. Cancels, cancels, so we get a half minus a half, which is just a, negative a. So I'm not too handy with the signs there. And I have a half equals negative a absolute value a squared. Those, of course, cancel out. And what I get is that a squared equals 1/2, or a equals 1 over square root of 2. And we're only concerned about the positive solution there. And there we go. That is our normalization constant. Not so bad, actually fairly reasonable. Let's go ahead to part B. Let's pull up the problem again. Let's see this one. So this is a super long problem. I think it went up to like part F. Okay. B. So now we have our particle trapped in the cell well, has an initial wave function, which was a mixture of two stationary states. We normalized it. I'm going to write my result because it is going to be very easy to forget. Also going to write out this guy. This is our general solution to a infinite square well in pi over ax. There we go. Now we want to find psi of x and t, and this guy. So we know the initial state, and then now we want to find the time-dependent factor of the state. And it does give you a nice little hint, which I'll admit that I kind of ignored. Not this Euler's formula. This is a very helpful formula, so I'm just going to write it out here because it's a little bit hard to see in the problem. I kind of, the first time I did this, I did not put it in terms of omega, and it is much more helpful to put it in terms of omega. So they're just defining the frequency, or angular frequency, if you prefer the term for omega, to just be pi squared h bar over 2ma squared. Now, I cannot emphasize units enough. Just because you're doing quantum mechanics doesn't mean that reality stopped existing. So this has units of 1 over seconds, or hertz. So this here, we have h bar is joule seconds. So a joule is a kilogram meter squared over second squared, but that's seconds squared on the bottom times seconds, so those seconds canceled out. And then on the bottom we had mass, so that's kilograms, and then we had the width of the well squared. The width of the well is always distance, it's not exotic, so that means it's meters. So that checks out. It's always a good practice to check the units. The units do still have to exist. This is the difference between physics and math. Okay. Now let's go ahead and use one of the results that we got earlier in the chapter, that we got from separation of variables. So I won't go over it again, but this is where it comes from. If you're not good with separation of variables, you really should be by the end of this course. Okay, so from our separation of variables result, which we did before, we know that our time-dependent Schrodinger equation is equal to our wave function at time equals 0 times an exponential time dependence factor. Okay, now let's go ahead and fill in our psi at x equals 0. So that was a, which is 1 over square root of 2, times stationary state 1, and then I'm going to go ahead and just multiply through this exponential because we have different energy states for each one. So I'm just going to call it E1. And then we have the same normalization, except this is going to be 2 pi. And this is going to be negative IE2. So the different stationary states do have different energies. They are times the same time, our general exponential time factor, but the energy in that term does need to be expressed differently. I'm going to just, instead of rederiving it, let's just write out the result of what our energy levels of an infinite square well are. And now you could very nicely clear up some of this notation here so that E, I'm going to try to convert my results into the nicer notation instead of writing all this pi squared over 2ma. So that's going to be n squared. Pi squared times h bar over 2ma squared is just omega, and then divided by h bar. So then we have 1 over seconds divided by joule seconds. So that we can get our let's see, no, we want to have, wrong way, that's why you check units, times h bar. There we go, 1 over seconds times joule seconds, and then we have units of energy joules. So when I put it back into the exponential, that extra h bar is just going to cancel out. So I can really make my life a whole lot easier here. And that's going to be 2 over a sine, and then E1 is just where n equals 1, so that's just I omega t. And I have my second excited state. And now there, n equals 2, so that's 4 omega t. Okay. So that cleared that up significantly, right? Now we can factor out some of these exponentials. So first off, we can factor out that 1 over square root. So these cancel. and then I have 1 over square root a. I can also factor out this term here. So I get e to the negative I omega t. That factored out completely from my first term, but not completely from my second term, because that one had a factor of 4. So then that's 2 pi over a x, and then we had e to the negative 3I omega t. So this is our first part. There is our first result. We found what our time-dependent Schrodinger looks like. It just looks like that. That's as simplified as we could go. We could put it in different ways, but that's as much as I'm going to go with it. Now I'm going to look at the absolute values squared. Okay, so here I am going to have out in front my 1 over square root of a is just 1 over a. Then I have this times complex conjugate. So I get, I'll go ahead and write it out here. So I get e to the negative I omega t, e to the plus I omega t, and that's just going to cancel out. Then I'm going to have this guy over a negative 3I omega t, but that's going to be times this with a positive sign. Now the exponential is going to cancel out from the last term, but we are going to get that cross term. I don't really believe in having like any sort of math balls here, so it doesn't bother me to actually draw out what I'm doing. So I'm just taking that term. So that's sine squared just my regular FOIL like I learned how to do in whatever grade that was, like I remember. It was a long time ago. And then we take this one. So that's going to be, I'm going to go and write this one first. I'm already trying to write small so it fits. And then that's e to the negative I omega. And then we are going to have that guy. So then we will have okay, let me check that against what I had before. Yep. Alright. Seems to check out thus far. Now let's try to group these together a bit to make this a little bit more palatable. Alright, I have my 1 over a. And I'm going to go ahead and put my sine squared terms first. Sine squared pi over ax. And then this guy. Sine squared 2 pi over ax. Then I have these two terms are the same, so I'm going to factor them out. Pi over ax sine 2 pi over ax, but I get e to the 3I omega plus e to the negative 3I omega t. And that is everything. Okay, now we're going to use that Euler relation that he told us to use in nice terms before. So if I have e to the I theta plus, say, e to the negative I theta, I have cosine theta plus I sine theta plus cosine theta minus I sine theta. So I can go ahead and replace those exponentials there. And my i's sine terms are going to cancel out, and I'll just get two cosine terms. So then I have 1 over a, my sine squared terms, plus these guys, but now I have a 2 because I had two cosines. And then that's going to be cosine of 3 omega t in bracket. And that looks a little bit nicer than the other way I had it, where I did not use that omega. So what we have is our familiar sine wave, but we have an oscillation in time. So we have this extra oscillating term on the end of it, and it's oscillating with like 3 omega. Okay. I would like to keep this result. And let's go ahead on to problem C, or part C of this problem. Of this very large problem here. Okay. So what we want now is the expectation value. don't seem to have been able to copy that. Let's go back and copy it again. I need this value in order to compute the computation, or the expectation value of x. Looks like I'm stuck just having to memorize it. Alright. So I had sine of xt squared, our absolute value is 1 over a sine squared over pi over ax plus our next excited state, and then our oscillating term. We had a 2. And then we had our cosine, and that was 3 omega t. Okay. Now we want our expectation value of x, and it is oscillating in time. That means we have to use this. We can't use the time equals 0 solution. That worked for normalization, but this is an expectation value. So this does exist in time. We have to use the time dependent Schrodinger. Now, you will notice that we're going to have to look at the amplitude of the oscillation. And if it's oscillating more than, the well, then clearly there's a problem there. Okay, our expectation value is just our integral dx, and then I can write it out like this. It'd be psi of xtx, and then complex conjugate. Or you could just write it like this. And that's why I needed that result. So our expectation value is our integral. We only need to integrate over the width of the well, because that's the only place where a particle actually exists. And then we have one over a, we'll just put in parentheses here. 1 over a, well, let's just put in our x, there we go, x over a, and this whole stuff. Now I'm going to make use of just doing those u substitutions again. So I'm just going to be making like the same exact u substitutions that I did before. And we can of course break this into 3 different integrals. So what I have is here my u was pi over ax, so my x equals u a over pi. So I'm going to get an extra factor because I have an x out there. same thing's going to happen with the other guy because each one of these terms is multiplied by an x. So I'm going to go ahead and break this up into 3 pieces. So I'm going to have 1, 2, 3. So I'm going to call that expectation value 1. So I have, and I'm keeping the a out for all of them. Like I'm just keeping the constant in there. So I have 1 over a, and then my limits are 0 and pi. My du, so du dx is just pi over a. So when I write dx, I get a over pi. My x is u a over pi, so those end up being squared. And then I have sine squared u. So that equals a over pi squared, 0 to pi, du, not dx, du u sine squared u. Okay. Now, so maybe I should have used a y there, because I'm going to integrate by parts. Oh, that's squared. So I'm just going to switch my u's to y's to make it a little bit more clear. Okay, now I'm going to go ahead and integrate by parts. So my integration by parts, so that's just where we have integral of u dv is going to equal uv parsed out minus v du. So in this case, my u is going to be y. So if I take du, I get 1. And then my dv is sine squared, because I already know how to integrate that. That is going to be y over 2 minus 1/4 sine 2y. So here, my expectation value of 1 equals a over pi squared, and then I have u times v, so that's y squared over 2, just put that in parentheses, minus y over 4 sine 2y evaluated at 0 and pi, so that just goes away, minus my integral from 0 to pi of v du. And my du is just 1. So that's my integral of this guy. So that's just minus 1/4 sine 2y. Oh, that's where that guy went. Okay, so that one goes away. The first sine term just goes away. So I end up getting a over pi squared, and then we're going to have pi squared over 2. this one, we get the integral of y half is just going to be y squared over 4. So if I evaluate that at the limits, I get pi squared over 4. Playing a little bit loose with the limits here, or sorry, the sign, but you get the idea. They are opposite sign of each other. And then the integral of 1/4 sine 2y is going to be 1/8 cosine. We keep so we had opposite sign, opposite. Cosine of 2y, which our limit was pi, so that's just cosine of 2 pi, and then that'll be minus, so I should put these in parentheses, minus cosine of 0. Okay, now cosine looks like this. So it starts here, goes this way. So cosine of 0 is 1 pi 2 pi. So 2 pi, cosine of 2 pi is negative 1. Oh. Whoops, wrong way. Cosine 2 pi is 1. There we go. Pi 2 pi. So cosine of 0 minus cosine of 2 pi, because it's even, that just equals 0. So we have pi halves minus pi fourths, or pi squared, but that cancels out. So we have 1/2 minus 1/4, that just equals a fourth. I really should have just done that to be proper, but I wanted to get a positive number, so I get a over 4. Okay, that was a lot of work for that one, but the second one is the same, and that's because it's the same exact function. All we have in there is a 2 pi, but all my limits, instead of being from 0 to pi, are from 0 to 2 pi. So what I would get out in front here is I would end up getting a over, I would just get a over 2 pi squared, 0 to 2 pi dy y sine squared y. So anywhere I had a pi, I would have a 2 pi. So I end up getting the same answer. I get a fourth. So we can skip a lot of that work for that guy. Okay, now x3. That one is going to be, we have our integral. We'll just write it here from 0 to a dx, and I have a 2 over a x sine this guy sine this guy, and then cosine 3 omega t. Now the nice thing about that oscillating term is that it goes away. Well, it doesn't go away. It comes out of the integral, I guess is what I mean to say there. So I get 2 cosine 3 omega t over A and then we have 0 to A dx and our two excited wave function states. Okay, now I'm going to use, I don't remember what the exactly what it's called, but let's say that's U, let's say that's V. We have a trig ID, which is very helpful, and we're going to use that. So we get cosine of U minus V minus, always have to make sure I look up the signs on this, U plus V. Okay. And that just involved me, like, honestly going on Google looking up trig IDs until I found one that was going to be useful. Okay, so now we have 1/2, so that's going to come out here. And dx, and then we have cosine of pi over ax minus 2 pi over ax. So that's actually, let's keep with positive numbers. So I'm going to say this one's V and this one's U. So I get 2 pi over ax minus pi over ax. So that's just pi over ax minus cosine of pi over ax plus 2 pi over ax. So that's 3 pi over ax. And now that's become a pretty easy integral to do. Now that is just definitely not hard at all to do. Oh, I forgot my x's here. And we just have x. There we go. That should have had an x. Okay, now we can do integrating by parts. So we have two different integrals here. So the first one, I can say u equals x, so that du equals 1. So that means dv equals cosine pi over ax. So v is the integral of that, so that's a over pi. Yep, same sign. Sine of pi over ax. So I'll say those are 1s. And then u2 was x, du2 is 1, dv2 is a cosine 3 pi over ax, and v2 is just the integral of that, so that's a over 3 pi sine 3 pi over ax. There we go. Okay. And this is using this guy, so u dv equals u times v minus v du. Alright, so we have cosine 3 omega t over a. That's just going to be multiplied by, let's do our first one, u times v. So u is x, v is this guy, and that's evaluated at 0 to a minus our integral from 0 to a dx of v du, this guy. And you'll see it's pretty repetitive for the next part. Now we get minus u times a over 3 pi. Of course, these sine terms you can probably already see go away. And then that's a plus. And a pretty easy integral, which is just going to be a over 3 pi sine of 3 pi over ax. So those go to 0. So my third expectation value is cosine 3 omega t over a. And then I just have a couple of cosine terms. So that's going to be minus, let's see, integrating sine gives us negative sine, gives us positive cosine. We get another factor of a over pi cosine, that's those parentheses, cosine of pi over a. So we have cosine of 0 minus cosine of pi. Then that was plus and then that goes to minus a squared, and then we get 9 pi squared, and then we have cosine of 0 minus cosine of 3 pi. We could have also written that as negative and then plus. You get the idea. Might have been a little bit more standard to write it the other way with the signs. So we could do negative plus plus negative. Oh, switching. There we go. Same with these guys. There we go. If that makes you feel better. Okay. At any rate, cosine of 0 is 1. Cosine of pi is negative 1. So I get negative 1, because I have that negative sign there. Here I get cosine of 0 is 1, so negative 1. That's odd, so that's negative 1. So what I get here is my third expectation value is cosine 3 omega t over a times negative 2 times a squared, so I just get 2a squared over pi squared minus, because they have different signs from each other, negative 2, so we have 2 over I got distracted for a second there, over 9 pi squared. Alright, so then I can pull out that 2. I could also pull out the a. I can pull out everything except for the 1/9. Okay, so I'm going to have 2 cosine 3 omega t, and then we're going to have a squared. Oops, that's going to cancel out with one of those a's on the bottom, over pi squared. And then I'm going to have 1 minus 1/9. So that equals 9/9 minus 1/9 is 8/9. So I get 16a cosine 3 omega t over 9 pi squared. Okay, now I'm just going to put this all together. So part C, if you forgot already, wanted to know the expectation value. So I had 1 was, you can see I've already forgotten, a fourth. Expectation value 2 was the same. Expectation value 3 we just did was 16a cosine 3 omega t over 9 pi squared. So then my whole expectation value, putting all those integrals together, we have a fourths plus a fourths is a halves plus 16a cosine 3 omega t over 9 pi squared. Now inside the cosine we don't have any units, pi doesn't have any units, we have units of meters, which we should have for our expectation value. So I basically have a plus 1/2 16, oops, I don't know why I put a there, cosine 3 omega t. Now for our oscillating term, we could also take out the 1/2. I don't know why we'd want to do that. I guess, so like it warned you to say like the amplitude should be less than a half. So let's just go ahead and factor out the a half. So our amplitude here, just on our oscillating term, 1 plus 32 cosine 3 omega t. I'm not sure if that really helps make that any more clear. Our amplitude is 16a over 9 pi squared. So that's less than 1/2. So 16 over 9 is just barely less than 1/2, but with the pi there. And then our frequency is just 3 times omega. Okay, so that's going to be the first part of this. The problem does go on, but I'm going to do D, E, and F in a different video.